Okay. Good morning, everyone. I have to say that I'm impressed by the number of people who came to the lecture this morning. I was expecting that everybody would be asleep still. It was a pretty heavy weekend, sport-wise. Okay, so I'll be continuing a little bit what I did last classes, but these two classes will be mostly self-contained. And my idea here is I'm going to give you, in a way, a few tools to analyze non-equilibrium systems governed by SDEs. And these tools were things that up to recently were kind of more theoretical. But recently, with machine learning, many of the objects that I will be introducing can actually be estimated from data quite efficiently. Okay, and so the first part of the class until the coffee break will be mostly theory on the board, and then try to bear with me. The next class after the coffee break, I'll illustrate all that on one example, which is motility-induced phase transition in a system of interacting particles, where I'll show you simulation and images. Okay. But the first part of the class will be on the board. And I think that the object that I will be introducing here will be used in particular by Marc Mézard later in his classes. Okay? So let's start with a little calculation. Suppose that you have a dynamical system that's governed by an SDE. So for the moment, I will assume that this is time independent and that sigma is just a real number. It's simply to make the notation simpler. Xt will be a vector in Rd, and more generally you could consider this in an Hilbert space, but we'll do that later. This is the Wiener process, and then I'll add a square root of 2 here. This is to avoid having to drag on factor 1/2 later on. Okay? So we discussed, this is a stochastic process. It doesn't need to be in detail balanced, so this B here doesn't need to be minus the grade of a potential. Okay? And we know that we can look at the Fokker-Planck equation, also known as forward Kolmogorov equation, which is, so it's a function of t and x, and it satisfies this continuity equation. Right, this is things that we discussed last time. And this is the Laplacian, and D is just sigma square in this case. More generally, it's going to be sigma transpose when it depends on x. Okay, and typically you need to solve this equation with some initial condition, which is, what was the distribution of x of t at time t equals 0. Okay? So there is a way to make a little calculation that is very simple, but will lead us to somewhere interesting, which is that I can introduce a new PDF, which is rho t, I'll write reverse, which is equal to rho of t minus tx, where t here is any number. For the argument that I'm going to take, let's just take it to be positive. Okay? And so you can write down an equation for this guy just by looking at this one. And what it satisfies, let me drop the x dependency to go a little bit quicker, is just this is the same equation as above, except that you change the sign, and here, suppose that you evaluate that guy. What happens is that at time t equals 0 here, this should be the other one at time t equals t, right? And the reason why I do that like that, so you notice that this equation is a bit unpleasant because you have turned a diffusion equation into an anti-diffusion equation. Okay? But there's a little trick that you can do, which is that you can now rewrite that like this. And this trick we're going to use repeatedly in the class. So I have used a little identity here that I'll write above in green, which is that the grad of the log of rho RT times rho RT is simply this. Okay, and this identity, if you use it here, you realize that, okay, so this term, the B is the one you want. This guy here is just a way to write the gradient of rho R. Then there is a divergence of this gradient, give you the Laplacian. So you have minus twice the Laplacian here. And then you have plus 1 time the Laplacian here. So these two lines are identical. Okay, it's just a rewriting. However, this is at the level of the PDF, but once you have written this, you realize that you can now write something which is called the reversed time SDE, which is, let me write that. No, this guy depends on time, even if the other one, though this is going to be just for a minute. So now you can write this, right? We have introduced a new drift, which is BR of x, which is, what is that guy? Well, it's minus B of x plus twice D times the gradient of the log of rho RT, which is also rho of capital T minus T, okay? And that depends, and the, okay? And so these two guys are, these two guys are the same, right? And in fact, these two are the same because at the end of the PDF, I'm just rewriting it in a different way. But this SDE and this SDE have different path in general, right? In particular, what you have is that if you think about what this is a process that has the same law as this guy. In law or in distribution, that's what we write like that. Okay? So what this guy is, in a way, is that, so you could imagine that you generate a trajectory from this, or many trajectories, okay? And then you would play them in reverse. If you play them in reverse, well, instead of doing that, you could have done something equivalent, which is to generate many trajectories here, starting them with this initial condition, which is the PDF of the other one at time t minus t. And what you would see then generated directly is the time reverse of this one. Clear? Okay. So this becomes interesting if you are at a statistical steady state. Statistical steady state. And then I'm going to distinguish between non-equilibrium statistical steady state and steady. So what is steady states means what? These mean that, so let's do that with another color. It says this is equal to 0, and so then this is equal to 0. Okay, and it also said that you get that the rho R of t is equal to rho of t because they are both equal to a rho which is independent of time. This is the steady state solution of this equation, assuming it exists. Okay, and so if you do that, well, here, this becomes this same rho of x, which is, this steady state solution, right? And so now you have a characterization of equilibrium, which is, or non-equilibrium, when will you not be able to tell whether the movie that is being played of the trajectory is the time forward or the time reversed? Is if this is equal to that, right? Because then there is nothing in this equation that is different from this one. It's just a rewriting. Okay? So the question is whether, is whether you have that, you can ask yourself, is this relation true? Again, on a steady state. If it's true, it's equilibrium, because it means that BR is equal to B. If it's not true, it's non-equilibrium. It means that there is statistical information in the trajectory that allows you to tell whether you play them forward or backward in time. Okay? Right? All right, so maybe let's make a little exercise. Let me erase this to see. Let me keep that. Okay, let me keep this equation. And this is an if and only if condition, right? Like there's no other way to be at equilibrium. So suppose that, this is the equation that we are talking about. Well, the typical case of the equilibrium is if you take B of x is equal to minus d times the gradient of a potential. Because in that case, you know what rho x is up to a normalization factor. So I'm working in units where the temperature is 1, right? And you can check that this condition here is satisfied. Okay? Like, let me check that I'm not forgetting anything. Right? Okay? And so, but as I say, in general, this will not be satisfied. So you're going to get, this is the typical, this is the canonical, well, actually, no pun intended, but canonical example of equilibrium system is this. Okay? No pun intended, because this is also the canonical density. But okay. So you see that there is there's another quantity here. Let me erase this. Right, which is, I have to rewrite that. Which is that if you have, so let me rewrite the equation. Should not have erased it, I'm sorry. So this equation right, can also be written as being minus the gradient of a current is equal to 0. Okay? This current is the one that you read from above, is Bx rho of x minus d times right? And you see that you can actually, you can introduce another quantity, which is v of x, which is simply j of x divided by rho of x. I'm making the assumption here that this division makes sense, right? And this guy is b of x minus, sorry, there's no log here, right? This is the current is just, the current is, the divergence. I'm using scalar. In a minute I will generalize that. But in the velocity now you need to put the log. And everybody sees that this is just by rewriting that the Laplacian is the divergence of the gradient that leads you to this. And this is using this identity, that the grad log rho times rho is rho to actually perform, you grad rho divided by rho is grad log rho. So you have this. So you have introduced this. So this is the, this is the current, the probability current, right? And this is what's called the current velocity. Okay? And you can see that this condition is equivalent to asking whether this is equal to 0. If the current velocity is equal to 0, it's an equilibrium state. If the current velocity is not equal to 0, you're out of equilibrium. Okay? And you can actually, there's another equation that you can write, like, which is this guy, and we're going to play with it. Which this is an ODE, so this dot is just d dt. You can look at this quantity. This is an ODE, where the flow lines of this equation are the line of current, of probability current. At equilibrium, this ODE stays put. There's no motion. But if you're at non-equilibrium, this moves. It moves, however, in a way which preserves the rho. In other words, if you write down the transport equation associated with this, right, which is, you can write the transport equation to associate with this simply like this. Well, at steady state, this is equal to 0. And this condition is automatically satisfied because if this rho is the same as above, what I have written here is J, and I have that the divergence of J is equal to 0. Right? And just to hammer the point, this guy is whether, so this is all about the fact that a steady state means that this is true. But of course, you can realize that with J of x that is not necessarily equal to 0. Which again means that you can have a current. Okay? Yes? Okay. And so this gives us like a way to, and of course, I'm going to be focusing on physical processes here. But you could actually try to do this for non-physical processes, and I think what Mark will be talking about is that if you go back to the fully non-equilibrium, where everything depends on time, you could imagine, for example, having samples of images that would be the rho 0 that you pass into some diffusion here that is sufficiently simple, like an ocean back, and then they devolve due to that into noise. And then somehow, if you were able to evaluate this score, this guy, he's going to be the score in a minute. If you can evaluate this, then you could get the V, or you could do the time reverse SD that's above. And so now you could go backward, which is you could turn, the image they've gone into noise, the noise into images. Yes? No, I'm not saying, I'm saying, so if V0J is equal to 0, you're at equilibrium. If V is not equal to 0, J is not equal to 0, you're out of equilibrium. But in that case, the condition is not that the divergence of V is equal to 0, it's the divergence of V rho is equal to 0, which is just the same as the divergence of J. Okay? Okay, so we have introduced here two K quantities, and I'll play a little bit with them, for a couple of minutes, which is we have introduced the score, that's the terminology, and we have introduced the velocity. Okay, so let me write them down, because I want to give you a little bit more interpretation of what these guys are, and also ways to estimate them. Okay, and this is the part where, up to not so long ago, what I'm going to be discussing here would have been deemed impossible. Like, if I had given this lecture in this all here 20 years ago and claimed that I could do what we're going to now discuss, you could have walked off saying, this guy is mad. But it turns out that these days we can do it. So there is two quantities that we want to, I'm going to discuss them. First, the score, this is the terminology that's given to this. And let's go back to the general case where this could be depending on time. Okay? So there is this little identity that you can derive, namely that, okay, so the tools that have changed in the last 10 years are the tool for machine learning. What's machine learning at the end of the day is just a way to, how do you use machine learning? You write an objective function for that guy that's tractable. What does that mean, tractable? That means that you can express it as an expectation that can be empirically evaluated on data. Okay, so let's just do that, right? So first notice that, suppose I introduce this guy. We are working on RD. So let's introduce, a loss for a quantity that I call S. A loss, so I'm using the terminology. So let's look at this guy, and let's view this as an objective for S of t. This is called the Fisher divergence by a statistician, this object. Okay, so well, clearly, if, and let's, I'm going to repeat this a few times, then at some point I'll forget, but let's imagine that this is true. Then the unique minimizer of this objective is S equal grad log rho, because this is convex, and it's 0 if this guy is equal to this guy. And if you add the fact that this is positive, it's strictly convex, and so this is the only thing that can happen. Now, this is an expectation, so that's kind of nice because, this guy I'm taking expectations. That's nice because in principle, expectation can be estimated on empirical data. But unfortunately, it's the expectation of something that contains the unknown. That's not useful. But you can do this. For simplicity, let me eliminate all the dependency. I'll just rewrite it. Everything depends on X, but I'm writing it using, dropping that dependency. Just to be a bit quicker. So you have this. I have rewritten the objective as above. And now you notice the following thing. This guy is a constant. That means that there is no ST, no STX. That means that if you drop it from the loss, you change the value of the minimum, but not the value of the minimizer. Okay? Because the critical points are exactly the same. And now this one is a little bit problematic, but you notice that, I'll write it above so they have a bit more space. If you look at this guy, but you notice that you can undo what we did. The grad log rho times rho is grad rho. And then if you integrate by parts, you can rewrite this whole thing as being twice the divergence of STX, ST times rho t. Yes, this is undoing this grad log rho rho equal grad rho, and then integrating by part. And now you see that you can rewrite this loss. It's not the same. Okay, so let's put this one like with a little hat, and now we're going to rewrite E of ST. And I'll rewrite it as an expectation, where the expectation is over the, this guy, there's an SDE associated with it. In fact, this could depend on time. And here the sigma could be something that also, let's put always but this could be, a diffuse, something that is non-diagonal and non-scalar. Okay, and that's the PDF of this object. And it could be time dependent. Here we don't care whether we are at a steady state or not. So this expectation will be over that process, and it's the expectation of what? Of ST xt square plus twice the divergence of ST xt. The divergence. Okay? And this is now a loss that is completely expressed of an expectation of the unknown. And so that's amenable to estimation. In the context of images, this would be the image that you noised, right? The one that you pass to the Sörsenberg process, so that you take the image, you exponentially squish the signal and you replace it exponentially with Gaussian noise. That would be that, right? And what I'm going to do in the next part of the class is to say, well, here we're going to use all the new toolbox of machine learning, which is that we're going to put a big neural network to estimate this, to approximate S, and then we're going to view this loss as a loss for the parameter in this neural network. Notice that I could also do this, view that. It doesn't really change anything if I do this. I could evaluate this ST pointwise in time, but again, also is the same argument if you were to time integrate that on any t that's bigger than 0. You could also, look at this guy, and here you have a loss that is for the function st of x. Right? That means that you could have one big neural network that depends on parameter that represent this function not only on space, but on space and time. Next class we'll do this. Okay? And I think for most of, from the poster presentation, I think many of you are familiar with this already. Okay? Right. That's one thing. Now, I need that guy, so let me keep it, same as the E here, right? And here, I have sigma of x is like d, d, and the d of x is sigma. It doesn't matter. You notice that this doesn't matter at all for the way this class has been phrased, but it matters for the way you would generate the data, okay? And maybe I have said that, but let me say it again. You have seen that for images of core-based diffusion in the context of image, but this is completely general, right? You can also do this if you have, if this is the SDE governing the dynamics of your favorite physical system. Okay, that's what we're going to do next. Okay. Now there was this other quantity which is V, right? And okay, I need to rewrite a few formula. So the other quantity that we introduce is this V of x. Let's write it. And in general, it depends on time. So it's a V of x, which is bt of x. Everything here could depend on time. I don't know if I want to do that, but like we can. It's so sorry. In general, when you do contraction with tensors like that, you need to be a little bit careful about whether it's a tensor or it's transpose. But that guy is his own transpose, so there is no difficulty here. So we're gonna, we're gonna look at this, and remember that this is also, by definition, the current divided by the PDF. Okay. Now I want to write a loss for V. So here is something that comes in mind. This is a quadratic loss in V. If rho is positive, it's strictly convex. So it has a unique minimum. And what is the minimum? Well, it's V is equal to J over rho. Yes? Do I need to write what J is? J is V times... okay. J is B times rho minus D grad rho. Right? Yes? Everybody sees that this is a valid objective for V? Okay. Now, let's do the same thing as there. And here... They didn't matter, but here it will matter. Let's time integrate this. Then there's a little identity that you can prove. I tried to upload the notes this morning, and I will upload them. I've written all this, and there's a proof of what I'm going to show you now, but I don't want to... I'll explain in word what it is, but it is written in full in the node, but I couldn't manage. This term is this term, right? Because by definition, rho t is the PDF of this guy, and so taking the expectation over this test function is just taking this. It's the same. Now the question is, okay, and I have forgotten. Maybe I should put it here. The question is, what's that? Well, you can convince yourself that this is this. It's this integral. So it's a stochastic integral that involves the process dxt, and that is Stratanovich. So what does that mean? That means that if you were to, the t there doesn't matter, but if you were to want to evaluate this numerically, what you should do is this. If h is a small time step, discretization time step, what this means is that you are not evaluating. So in the Ito convention, when you have a product, you always evaluate it, the argument in a way which is non-anticipative, meaning that you would get xt, and this one would be xt plus h minus xt. When you do Strato, you replace that by the midpoint rule. Okay, and as you can see, this is, and maybe that's why maybe that's what makes intuition physically. This is the one that is time reversible, in a way, because there's no direct t plus h, and t plays the same role here. Okay, so this is a loss. I'll write it. I'll write it as an e, and this is an e for v. Okay? Let me make a few remarks about this. So this, in fact, is somewhat more general than this. Right? I'm going to write something here which is, let me erase that and try to insist a little bit about this. If formally, let me make a little calculation. So as I say, in the note that I will be sharing with you, hopefully, when we can upload it, there is an actual kind of proof using stochastic calculus of the fact that this is equal to that. Okay, or more appropriately, that this is equal to that, right? But roughly speaking, you should think about this loss. Roughly, I'm going to write it like that, a little bit sloppily, but you should think about this you can't quite do that, right? I cannot write something like this because this xt is in general not differentiable. But let's pretend we can, okay? Then the loss that I have written here is just this, right? And then, so there is a way to rewrite that guy using the Tower property of the conditional expectation. I can always rewrite that as being xt conditional on xt. This is the conditional expectation. And the Tower property says that if you take the conditional expectation and then you take the expectation, that's the full expectation. Okay? But if you write the line like that, you can also write it like this. So this is dt. Then I'm going to put a dx. What is this conditional expectation is multiplied This is just rewriting what the expectation is. Yes? And here, there's always these two meanings to the conditional expectation. The conditional expectation can either be a random variable, that's what it is, or it can be a function, right? So this is, conditioned on the value of the process. This is conditioned on the fact that the process takes the value x, right? And now you see that if you look at that, what is the minimizer here? Yeah, what is the minimizer? Well, is Vt, is just completing the square. So this velocity actually has a very simple interpretation. Right? Is the conditional expectation of x dot at the given location, where this conditional expectation, where what is expectation over is over the PDF. Okay? And this is telling you, well, actually, this doesn't make quite sense because these are non-differentiable processes in general, but you can give it the meaning as a stochastic integral, and that's this. And this is, again, amenable to estimation. If I have realization of the SDE that I have now erased, sorry about that, you can empirically estimate this. And if you can empirically estimate this, you can, in principle, minimize it over a class of V that is rich enough to be expressive enough, and that's a neural network. That's what we're going to do next class. Okay? Now, I want to discuss physics, but there is a case where, in fact, this is even, we are talking about SDEs here, but you notice that there is nothing here, that requires this to, I should not have erased the loss, but it's still there. We could, if I write if rho t satisfies this continuity equation, okay, and it is, so this is a conservation law, and we assume that the conditions are met so that this will automatically, since this is a conservation law, this will automatically preserve the integral of rho. Because if you integrate this is a divergence, so it goes away. But suppose that J has the condition that if rho at t equals 0 is positive, it remains positive, so that it can be interpreted as a PDF. Okay? Then, if you define, you forget about this, you just say this is Vtx. Then you can rewrite that guy as being Vtx times rho tx, a bit of a tautology. But this offers a lot of possibilities. In particular, and I'm not going to discuss that, you could imagine that you introduce, let's introduce the following process. Where, imagine that x0 is a draw from a certain PDF rho 0, and x1 is a draw from a certain PDF rho 1. This stochastic process here is not a diffusion. Actually, it is time differentiable, it's smooth, okay? And what is the property of this guy? So, so it's a process. Why is it random? Because this is random and this is random. You have two distributions, and you pair points, right? And then you take t here in between 0 and 1 to go from one to the other, okay? Then, this is stochastic process because of the randomness here. But you can actually find out what is the velocity that's associated with it. Because in this case, this formula makes complete sense. Because x dot exists. What's x dot? Is just x1 minus x0. Okay? And so you can, in that case, for this specific example, you can use this loss here, where the expectation that you need to take is over rho t, but that means it's just over realization of this, which are trivial to realize. Okay? And the Vt that you get would give you a transport or a probability flow that then transport x0 to x1 or x1 to x0, or sample from here to sample from there. Okay? So this is something that, with Michael Albergo and Nick Boffey, we call stochastic interpolant. It has also been, known under the form of flow matching, which, and it's a generalization, if you wish, of score-based diffusion or diffusion processes. that allow you to connect two arbitrary distributions in finite time without bias, okay, and where all the estimation is the same or similar, okay, and where what you estimate is directly V. You don't estimate the score, you estimate V. Of course, if you have that guy, you can estimate the score from it. I'll discuss that maybe another time. I mean, this is like, or you can ask me offline. Okay.
Sorry. So that this is more general than the diffusion?
Yes.
I guess the diffusion is special case. Which one of the two is the...
Is a Gaussian. There's two issues that with diffusion. I mean, issues, like, you know, they are really the first. You know, there's a breakthrough in this paper by Ehrman and Song where they realized that there was a way to reverse this process. But now, in retrospect, you know, when you analyze it, one can be a little bit critical. There's two issues. One is that the base distribution that we use always needs to be Gaussian because you devolve into a Gaussian. You could, in principle, use other stochastic process to devolve the process to something else, but then it would not converge fast to it, and they would all hell would break loose. So they just put noise, you know, like ocean and back. And then there's another problem is that there's a matter of bias, that you, in principle, you should run that process up to t equal infinity, whereas here you don't need to. Okay. Though that second point they are catch, as we discovered from the work of Giulio and Mark, and he will probably discuss about that tomorrow. All right. So okay, so this is like, you know, we have done a bit of estimation and interpretation of these objects of the score. Now I want to kind of go back to physics and explain maybe to you what we can do with this, okay? And I will discuss maybe, depending on time, I'll discuss two things. I hope, well, first that I want to discuss is stochastic thermodynamics briefly, and then the second one is, if I have time, is fluctuation theorems and Jarzynski equality, but I'm not completely sure I'll have time to do that one. And you will see that there is a way. Okay, so bear with me. All right, let me first discuss stochastic thermodynamics, which, you know, there are experts here in the room. So, and you know, there are many people that have worked on that, but, you know, it's really, I think, Seifert who first introduced this, okay? So let's, you know, again, to fix ID, let's think about a process like that, and I'm going to go back to the time-dependent case because I would like mostly to discuss cases where you have a steady state. Though, as I say, everything can be generalized to non-equilibrium, which is non-equilibrium and out of steady state. But we will discuss about this, and we will assume that, you know, it could be equilibrium, but non-equilibrium statistical steady state with a PDF rho of x. Okay. All right. So if we look at the Gibbs or Gibbs-Boltzmann, let's think a little bit. Okay. So we know for a process like this, right, that essentially, you know, a key quantity is this v of x, this current velocity, because it allows you to do two things. First, you can verify whether it's equal to 0. If it's equal to 0, it's an equilibrium steady state. And if it's not equal to 0, that means it's non-equilibrium because there's current. Right? Now, what I want to explain a little bit is, of course, you could look at this current, and in the next lecture, I'll show you example where you can actually look at the current, so you'll see a little bit what happened in non-equilibrium system. But I want to explain maybe a little bit more what you can do with it from this viewpoint of stochastic thermodynamics. Okay? And there are many calculations like that you can make, so I'll just do one for illustration. So suppose that you look at the Gibbs entropy, or Boltzmann-Gibbs entropy, which is, you know, this h, which is minus the integral over Rd of the log of rho of x. Rho of x is this guy. Okay? In general, you know, for processes that relax to a statistical steady state, there's an H theorem for this, right? But here, you know, we will assume for this specific class that this is equal to a constant. You know, all the entropy has stopped. This entropy has stopped increasing because there's no time dependence anymore here. Okay. Okay. So you can introduce something which is called a stochastic entropy. The stochastic entropy is just taking minus the log of rho of xt. Why? Because if you take the expectation of this over the process, assuming that it's an equilibrium steady expectation, this guy gives you that. Right? But you can make a little calculation with this, which is that you can take the d of this, okay? And then, what is that? Well, okay, so this is this times this. Where again, this is a Stratanovich product, right? These two mathematical concepts of, stochastic integral, they typically mathematician likes to work with Ito, because when you have Ito isometry and Ito calculus. But Stratanovich is actually simpler because that's the one for which the standard rule of calculus applies. So you can actually write this. Now, of course, if you were to rewrite that as an Ito product, there's additional term that come about. But let's forget about that. Okay? Now, if you look at this, right, and you remember that this current velocity, let me write it here. Okay, like, I'll write it a bit, again, a bit sloppily, that this guy is actually the expectation, where now this is of x dot at xt equal x. Right? You see that you can if you take the conditional expectation of this, right? Take conditional expectation at xt equal x. Take the conditional expectation at xt equal x of this object. What do you get? Well, you get minus the gradient of the log of rho of x times this v of x. That's right. Replace this by x dot. So if you want to do that again, you need to put integral into. But this is you use this as a test function, and so you get this quantity. So this is this guy is what's called. It's a generalization. Is the system EPR. So we're going to be discussing about EPR. So this is the system EPR. EPR. Let me not write it. EPR is entropy production rate. So if you look at what, let me make a little box around this. Okay. So what is this quantity? Well, is the quantity that has the property that if you look at h dot, which is equal to 0, it is in fact, that guy, if you take this quantity and you average it over rho of x dx, if you undo all that, it actually tells you, so this is the entropy production rate, and it's this is not exactly the way it's defined in Seifert, but it does something which is very close. This is a function of x. So it's essentially, what this velocity allows you to do, because of the definition through the conditional expectation, it allows you to understand how, on average, things are evolving if you zoom at one specific point in state space. Okay? And so what this is saying, it's saying, and I'm going to show you an example in the next class, that in general, in a system that has reached a steady state, say non-equilibrium, there is no global entropy production, but there can be local entropy production. Meaning that along the trajectory, along the trajectory of the system, sometimes there are fluctuations that increase the entropy, sometimes there are fluctuations that decrease the entropy. Okay? And this, you can either think about it about a long time, or, and that's more informative, you can zoom at a point in state space and ask when the system reaches that point in state space, is it there increasing or decreasing its entropy on average? This is what this measures. There was a question over there. Right. Yeah. You'd like to have this? Okay, but you can add it because that one is not, I mean, that's an expectation of something that you put in. Okay, so you could add it. But maybe more to the point, let me go to the next step, because like there is a way to rewrite that in ways that I think might answer you. Was just one calculation. You're right that you know, this is a little bit too much mathsy, and there should be something which is where instead of using this entropy, you should use the Kullback-Leibler divergence, right? Or the cross entropy. Let's get to that. Okay. Yeah, I mean, they came a bit earlier, so that's why. Right. But okay, let me make one little calculation. Assume that let's again take the case that d of x is just a d, and let's assume that it's invertible. Otherwise, what I'm doing now won't work. This doesn't require. I forgot to say that, but this system could be hypoelliptic, meaning the noise here could only act on certain degrees of freedom and not all of them. It would still apply. What I'm going to do now requires something which is a little bit different. Okay? So you notice that you can write this. You know, we have this identity. And so if d is invertible, you can rewrite that by saying that the grad of log rho of x is equal to, okay, let me try to not mess up my signs, but it's, okay, I'm going to do a minus because I have a minus there anyway. So then it's v of x minus b of x, and then it's d minus 1. In fact, it doesn't really matter that d depends on x or doesn't depend on x. It's just, what really matters is that it's invertible. Okay? And if you do that, you see that you can rewrite that this cis can be rewritten as, so, you know, if you just plug that there, there is something which is v of x squared d minus 1 minus this just means v d minus 1 v. Okay, it's if you were to replace the b by a v, you would get. So you can write, you know, it's an identity. Okay, and you know this is, and here, you know, you will probably know much more than me because there is a decomposition which is, this is called the total entropy, production rate, and this is called the medium entropy. So it's a decomposition, and it's not completely apparent why this is written like that here. I'm going to give you one more interpretation in a minute, but if in this problem here, there's a certain number of special cases that you could consider. One I'll try at the end of the class, but I'm not sure I will have time, is where this is the grain of a potential, but the potential depends on time. And the other one is there's one part is the grain of the potential, and then you add a non-conservative force to it. In this case, this formula simplifies because there are identities that you can use because of the grad, and it makes better sense as to why this is the medium, because the only thing that appears here would be this non-conservative force. Okay? But these are two other quantities that in principle you can calculate by using the velocity. Now, I just want to show you one, I mean, I want to focus on this to give another interpretation that, you know, and then we'll see if we want to do more. So, sorry. You remember that there's this guy, and then, you know, I wrote this quantity. There was a BR. In this case, the BR is also independent of time, which is the time, you know, this is the SDE, and this is the time reverse SDE. Okay? And the BR here, just to recall, it's minus B of x plus twice d times the gradient of log rho x. And I think that this means that it is b of x minus 2vx. Let me double check that. It should be I mean, this is trivial algebra, but let me double check rather than re-deriving it. Sorry. Yeah, this is the same. I mean, if you use the definition of the V, these two guys are the same. Okay, this BR is expressed like that. That's the one we derived at the beginning, very beginning of the class, but you can also express it like this. Okay, and now this is not very important. It's important for, to do the calculation. I'm not trying to do. So what you could actually do is, going back to, you could actually look at the cross entropy, or the relative entropy, or the Kullback-Leibler divergence between the path measure of this process and the path measure of this process. Okay? So I'll write that like this, is that you take a certain interval of time, right? And instead of looking at rho, like the PDF, which is just looking at where the process is at a given time, you actually look at, it's the statistics of path with initial conditions that are taken from this. Okay? And then you can calculate, the cross entropy, so something which is like this. So it's PT, and then, okay, so, I mean, what I mean by this, and you can give it a meaning, is really like, this is the cross entropy relative to the reverse process of this guy. You could change it. You could put a PR here at the end. It's right. You can look at this quantity. Okay, and clearly, let's think a little bit. At equilibrium, these two path measures are the same by definition, right? Because B is equal to BR, so I'm rewriting the path measure associated with this is the same, right? This is why this form is useful. If V is equal to 0, you see that BR is equal to B. But if V is not equal to 0, these two guys differ. Okay? And what you can show is that this is that. Well, okay, I'll write it, like this, but it's this, this S dot that was there. The T just come from, when at the end of the day, so the way you would do that, and I'll put it in the note, I have not put it, but essentially you can use Girzanov theorem to compare these two processes. And then this is the Girzanov weight. You take the log, and then you take the expectation with respect to one of the process. If you do that, what you crank a little bit the machine, you realize that what remains is exactly this. Okay? And so, okay, you could also put it like, this 1 over t here. So you could take the limit if you want. It would also mean that the initial condition doesn't matter. If you were to take t going to infinity of this guy, you would get that it converges to this, where this would then be the non-equilibrium statistical steady state it converges to. Okay? This quantity, I forgot to say that, but obviously this one, because it's a square, is always bigger or equal to 0, which means that its average is not equal to 0. Right? So sometimes I think physicists prefer this because they'd like to have that entropy keeps increasing in non-equilibrium system, whereas with this Boltzmann entropy here, it sort of doesn't, Boltzmann-Gibbs. So here it does, and you would get that. And how would you calculate it? You would calculate it like that. So that's another interpretation of that. And this is an instance of what's called, Crookes fluctuation theorem, where, again, I'm going to stick my head out here because they're probably, better expert than me than this. This Crookes fluctuation theorem is something that allows you essentially to compare a process towards its time reverse. Okay? And the problem is that when Crookes derived this, he derived it as a generalization of Jarzynski equality in a very specific case, which was the case where B here was minus the gradient of a potential, where the potential depends on time. And the non-equilibrium nature of the process was the fact that this potential depends on time. Okay? And in that context, finding what is the right time reverse process to actually use this formula is kind of obvious. But these now have permeated the literature on non-equilibrium statistical mechanics. And for example, people are trying to use that to, for example, for interacting particles, like the one that undergo MIPS, motility induced phase transition. People want to use these things to try to calculate the entropy production rate. The difficulty is that in that case, it's not completely clear what the time reverse process is. In fact, it is completely clear what the time reverse process is this. But at least, but that one is not easily, in general, if you want to do pen and paper calculation, this is not an object that is easy to deal with because you don't know rho, right? Remember that, in a non-equilibrium statistical state, this is like a big. But what I'll show you in the next class is that, okay, so if you forget about pen and paper calculation, the pen and paper calculation leads to this, and then you say, well, what I need to know is that, and then you go back to the loss before, and you say, let's just calculate it. Then you can actually look at what's going on using the proper time reverse diffusion. Okay? Okay, so let me maybe now, do I have time? I have 25 minutes, right, or 20. All right, so I'll discuss maybe something a little bit different, which is another instance of, it's another fluctuation theorem. So I had, in the note, there is something about fluctuation theorem in general, and then there was Jarzynski equality. Okay, I'll do the general one, and the one for Jarzynski equality. With Jarzynski equality, if this is a generalization of Jarzynski equality, I'm going to discuss something which is slightly more general, just to explain to you something that can be done again with this, with this idea. But I need to be a little bit quick now. Okay. You notice that I slowed down the pace with respect to the previous class tremendously, right? Following advice from the audience. Okay. So let's do fluctuation theorems. Okay, so there will be something here where, maybe there's a bit of a lack of motivation, but I'll try to give it a little bit. So suppose you have a process like this again. Okay? And here, we're going to again assume that there's a steady state, but for the moment, it doesn't matter. And let's imagine that we are interested in calculating something like this. So take this guy, I will remove it in a minute. So here, f of x is a function that goes from Rd to R. It's a test function, and g is a vector valued test function that go like that. Okay? Suppose that I want to estimate this expectation. It could be, starting at a given point, but let's forget about that. Like, this would be conditional on where you start here. Forget about this. I want to estimate these guys. Okay? If you do large, fluctuation theorem, you can do, there are large deviation principle. In general, what you would really like to look at is, for example, if this limit, you want to compute things like this. Okay? Why is this useful? I don't know if Jorge will give a lecture on it, but it's useful because by taking the right f and the right g, you can actually probe, for example, things like, you can probe dynamical quantities in the system. Okay, for example, the activity, right? And what's happening here is that if you take the right f or the right g, or for example, you scale them by a big number, what happens is that, okay, so what is the difficulty into this is that it's something that allows you to probe the dynamics of your system by putting, the right f or the right g. But in general, it's kind of a bit useless to write it just like that, because if you try to do it numerically and you simulate this, then on this vanilla, and you use, as vanilla estimator of this, you just take an empirical expectation over that process of this guy. What you will get is that this vanilla estimator has dramatic variance. I mean, so it's a very bad estimator. Okay, and in fact, the more interesting is the quantity you want to look at. Typically, the worse this vanilla estimator is. Right? Is this something? Maybe I need to write one little thing here. I don't want to lose everybody. You know, there is something which is called Vanden lemma, which is a way to do large deviation, and it's something which is like this. Suppose that you have a PDF, row of X, okay? And you want to probe the tail of this guy, right? Typically what you would do is you can look at this integral. In general, this is, a dot product. You look at this. This is, the expectation of e to the lambda times x, where x is the realization of your row. Okay? And this allows you to do large deviation because in some sense this is tilting your measure. And if you take lambda either large positive or large negative, this expectation here is dominated by realization of x that are atypical in row. Think about this, for example, being a Gaussian. Okay, that's centered at 0, and then put that in, and you will realize that the typical realization that will contribute to that integral are the ones that are being shifted at the mean that goes to lambda, right, completely, right? So it's a way to probe rare events, okay? So this is, if you do it, this is on RD, right? This is on RD, and it's called, if you take the log of this, and then you take lambda minus 1 of that, right, which is like this, and then typically lambda is a vector, so you need to put, you do that, and then you put epsilon here, and you try to calculate the limit as this guy when epsilon goes to 0, right? If this is a limit, there is this is what's called Gardner-Ellis theorem of large deviation, and it's an instance of something more general, which is Vanden lemma, and allows you to calculate rare events, and and clearly, if you want to try to do that computationally, you can't simply pick realization of rho. Think again about a Gaussian. If you were to pick, Gaussian and lambda, this ratio is 200. This is dominated by events that are very far in the tail that you would never see. So you need to do something else. So this is exactly the same thing, if you wish, but it's a generalization where you do it in path space. Okay? And you use that to probe. Next class, I think I have an example of that. So how do you calculate these guys? I hope the motivation was... so now I need to go a little bit quick. How do you calculate this? So in the note, I will remove that guy because it's going to simplify my life, but you can do everything with it included. You can introduce here a quantity A of t. Let's define this as A of t. Then A of t satisfies that dAt is equal to f of xt dt. If this term were there, I would need to add plus gx dw, and you would have to be careful that this w is the same as that one. Okay? Look at the joint PDF. Let's denote rho of xa. This is the joint PDF of xt at. What does it satisfy? dt rho t xa. Everything depends on xa. I'm using like this row, which is a little bit different, so that I can distinguish between to emphasize its function of x and a. Sorry, f. This is just the Fokker-Planck equation for this joint process, right? And if there was a noise in the definition of A, if I had included that guy, there would be the additional diffusive term in A and a cross term between x and A. But let's look at that for a minute, right? You notice that if I introduce that, then let's call this guy here, let's give this guy, sorry. Okay. Let's call this expectation I. I of t. You see that by definition of rho, you have that I of t is equal to the integral dx yes. Let's define this guy to be q hat of x, so that I of t is just the integral over x of that guy. So it's not a PDF. It's positive, but it's not a PDF. It's positive because this is positive. But this guy, right? So if I define, okay, let me write it like that, q hat x, so that now we have the identity with that I is just the integral of that guy. Let's take the equation above, multiply it by e to the a, and integrate it to write an equation for q hat. Q hat only depend on x. That's what I wrote on the other side. So this is because there is no a in these terms. So I can put the EA, the integral goes across all of the, the diversions, the b, and it's directly this and both these terms, and so I get the equation that's below. This one here, there's an EA there, so you integrate by part. That change the sign, you get back the EA, and so you get this. Yes? So this equation has a mass that is not conserved, right? Why is the mass not conserved? Well, the mass is not conserved because of this term, and it better not be, because otherwise it would not give you the expectation that you want to look at, right? But, okay, let's introduce one more. Okay, so I'll do it here. Okay, so we had this, and then the dA. Let's normalize this guy. Right, so if you do this little calculation, you will realize that this quantity satisfies, they are all depending on x, this, where I've introduced a lambda t, which is, there's several ways you can write it, but it's this. Okay, so let me first think a little bit about what happened here. If you try to write down an equation for this guy, right, you're going to get the term that involves the dt q hat, but when you have the dt q hat, divided by that, you get all of this equation here that is divided by this. But since this doesn't depend on space, you can put it in all of. So that gives you all of these terms. But then there's one more term, which is the one where you have dt of this. Okay? dt of this gives you minus this ratio times the dt of that divided by itself. Yes? But what is the dt of that? Well, you integrate that equation, is just what comes from here. So that gives you this term with this lambda. Right? So you can think about this as this lambda as a Lagrange multiplier that's enforcing the fact that this equation doesn't preserve the mass, but this one does preserve the mass. Yes? Okay. And now, if you look at this, you realize that, okay, so what is this, right? Well, this is also, I mean, it's the dt of this divided by itself. Yes? So this is also the d over dt of the log of the integral of q at x dx. Because if you take this, you get d over dt of that divided by itself, and that's exactly what goes back to, it's exactly the term that we needed here. Yes? But this is then what? This is d over dt. Remember that I of t is this expectation, I of t is this integral, so this is d over dt of the log of I of t. Right? And so that means that if you solve this equation, then where you calculate lambda in such a way that the mass is always preserved, then this I of t is equal to the exponential of the integral from 0 to t of lambda t dt. Because this is just solving this guy. Right? So you have obtained this expression. Okay? That's a fluctuation theorem, and in fact it's a large deviation principle because of the following thing. Suppose that this process reach a steady state, run it for a long time. Okay? Let me write this here. How am I doing with time? How much time do I have? Like 5 minutes, 2 minutes? 10 minutes? Okay. Right. So, right. So, suppose that, qt of x as t goes to infinity reach a steady state. Let's write it like a q star. I don't know. I will just q. No more time. This will only happen if lambda t will converge towards a certain lambda star. Okay? It's not guaranteed that this is possible. This is a condition that depends on what b is. So the original process needs to have a steady state, equilibrium or non-equilibrium. And it also depends on what you put as an f. It might not be that there is a steady state. But assume that the conditions are satisfied so that this is true. Then if this is true, you see that what's going to happen is that at long time here, right, at long time, well, this, you can replace it by lambda star. So this will become capital T times lambda star. Okay? And so then what will you have? You will have that 1 over t times the limit, you will get that 1 over t times the log of I of t, which is this expectation, and then you take the limit as t goes to infinity, will be equal to lambda star. And that's a large deviation principle, or large deviation. It's a large deviation result. It tells you what. And what is this lambda star? In that case, is this? Is the solution of this equation? Is the principal? Is an eigenvalue problem, as you can see, of a generator that has been tilted by the f, and this is the eigenvalue, and you need to look for the principal eigenvalue, which you understand by looking at this dynamically, and that gives you the value of the lambda star there. Okay? Now, how do you realize this? Well, one possibility would be that you go back to this extended process and you use it to calculate this expectation. That's an extremely bad idea. Why is it a bad idea? It's because you can see that this process doesn't see A. A sees the f of x, but this guy, there's no back reaction onto it. So what you would get is that this will remain, again, in general, this expectation will be dominated by rare fluctuation of x, right? And so paths that do something abnormal, and you can use it to probe these things, right? And this will not happen with this process. So there's something else that can be done, and this is Lecomte, I never know, and Kirschen, and I think a few others, but perhaps Tailleur, but I can't guarantee who were on these papers. If Jorge is not there, but he will tell you that, which is that you can look about this and realize that you can actually write that as a burst-depth process, which is that you simulate this equation. You go back to this, okay? You simulate this equation, except that at every time, you allow instead of having one guy that's evolving, you evolve a large population of them, okay? And then you add a twist to this diffusion, namely that in a time t plus delta t, these particles can either die or duplicate, okay? And they do that according, so you introduce, you do diffusion plus birth death, where with a rate of birth death, which is simply f of xt minus the expectation of f of xt. So there are many people here that are, interested in population dynamics. I think that this will be very clear, is that what you have is that if you suppose that you have a large population of particles, right? They are, if you were just to look at this equation, they would evolve completely independently, okay? And what you can do is so instead of making them independent, you calculate this expectation over this population of particles. That gives you a fitness baseline. And then the particle that have a fitness that's above the baseline have a probability to duplicate with this rate. And the particle that have a fitness that's below that, so that this term is negative, die. Okay, that's the burst death. And there are ways to implement this in a way which is clever, where the number of particles is exactly preserved as you evolve them, right? But it is a little bit tricky if you do this, because in general, in high dimension, the scaling is not very good. The number of particles that you need to have in the system to actually estimate this fitness, this average fitness, the baseline fitness accurately is in general very large. It's scaled exponentially, so there is a problem. Okay, but in the few minutes that remain, like now I only have 2, and then you can actually use similar trick that the one that I explained in the previous slides to actually imagine that we were to introduce, let's introduce a phi tx, which is the solution of this equation. I have 2 more equations to write, and then we all go to coffee. It's Q. I write it as Q. The reason why I didn't want to be pedantic, but the reason why this Q is Q and not rho is because this Q is not the PDF of that guy, right? Everybody has understood that because of the additional term. The PDF of that guy would satisfy with this without that, right? Yeah. Suppose that we do this. Suppose phi satisfies this equation. Then if I had the solution to this equation, you can forget about the birth death process. You can simply add a term in the equation. Forget about if you do that, forget about the birth death, but the diffusion that you use, right? You would need to add, okay, so let me put a minus here. You would need to add simply plus the gradient of phi of t xt dt. You would replace this burst depth by an actual potential of a force that's pushing the particle towards this unlikely region, right? And then again, and I'm finishing with this, sorry for, you say, well, I mean, this is a PD in high dimension. It's going to be hard to actually estimate. But you realize that you can rewrite that variationally by doing this. The Lagrange equation associated with this equation for phi is this, right? Just take the first variation of this and you will get the one that's above. you need to be a little bit careful with constants and all that, but you get that. Okay, but no, that means that if you, what is this? Let me rewrite this. SQT, that's right. Like previous class, I'm just checking that you keep paying attention. Okay, so this is what? This is the last formula I write. Okay, so, but let me write it like this. This loss is an expectation over this process. Right? So now, okay, so implementing this numerically is not easy. But in principle, if you know, there is a route which is similar to the score estimation, in which you can use data generated by the process using, you know, you can do that by small increments of time, using, for example, a birth-death process at the beginning, that you use to slowly try to learn what that guy is. Okay, and you can do that by continuity method also, by doing many copies where f takes value, you scale it by something that go from 0 to 1. And then you use this data to learn this potential phi. Okay, and when you do that, at the end, you can get rid, it's the same idea as learning the score or learning the velocity, where you use data generated by the process to learn something. It's a little bit more complicated here because it's non-linear. The something is actually used. And then you can do that. And of course, at the end of time, right, this guy doesn't depend. I mean, I put a T here because I was looking at this. But you're really interested in the one that do no longer depend on time. Right? Because you're interested at the end at the limit. Okay? So it's an iterative process where you would keep doing this by replacing your birth, death, or whatever into something which is a transport. Slowly. Okay? What I've discussed in the first part of the class with the score and the velocity, we have done and published paper about it, and that's what I'm going to talk about. You know, I will illustrate all that after the break. This is something we are working on right now. Like, you know, we are trying to do these things, and the results are promising, but there is nothing that's published. But this is not, the point is actually not, I mean, even though I will in the next class illustrate this on results that we have obtained, I think that the main message of the class is not that. Is really that to try to show you that, you know, this is just like the tip of the iceberg of things that you can do if you now decide that instead of, you know, thinking about these problems classically, which is pre-machine learning, you start to say, no, I can do sampling and learning. I use the data to learn something, and that's the philosophy is, well, each time try to write a loss, which is given as an expectation that's empirically accessible to you one way or another. Use that to learn whatever it is that you need to learn, and you know, work in suspension of disbelief, which is these neural network will do wonders for you, even if we don't exactly understand why they work so well. You will be able to learn these functions, and you know, the example from images is one instance where this actually works. But next class I'll show you another one where there's kind of good evidence that you can learn things that really look quite improbable that it's possible. Okay, so that's it for this class. Next class I'll do it on using slides to show you the pictures. Sorry.